Hello, AP Chem students, and welcome to topic 5.3, concentration changes over time. The learning objective for today is 5.3.a, identify the rate law expression of a chemical reaction using data that show how the concentrations of reaction species change over time. So, as a reminder, let's talk about the meaning of order. If the concentrations change by a factor, then for zero order, the initial rate remains unchanged. So again, we change the concentration of something, but the rate doesn't change at all. That's zero order. First order, if whatever you do to the rate, the same factor happens to the, whatever you do to the concentration, the same thing happens to the rate. For second order, the initial rate changes by that factor squared. And for third order, the initial rate changes by that factor cubed. When a rate law is written that expresses how the rate depends on concentration, this is technically called a differential rate law. Usually we just call it the rate law. Another kind of rate law can be written, and we call that the integrated rate law, which expresses how concentrations depend on time. So the form of this type of rate law depends on the overall order of the reaction. And it looks different. So when we did a differential rate law, all you see is a difference in the exponent, but you're going to see that there's major differences with the integrated rate law. So let's get into it. So we're first going to think about zero order reactions. So for a zero order reaction, the rate is constant. It does not change with concentration. The integrated rate law for a zero order reaction is found on the equation sheet. So here's the kinetic section. And the zero order rate law looks like this. So if I go back, it's this very top one here. Okay, so this is integrated rate law for zero order reaction. In this case, if we plot the concentration of A versus time, that will produce a straight line with a slope equal to negative K. So if we rearrange this form here that's given on the equation sheet, you can see that we get this, and this is the same as the equation for this y is equal to mx plus b. So the equation for a line. So your y-axis will be your concentration of A at varying times. Your slope will be negative K. Your time will be your x-axis. And then, of course, your y-intercept will be concentration of A at time 0. So most often, zero-order reactions occur when a catalyst is required for the reaction to occur. We also see them if you have one species that's in great excess compared to the others that are present in the reaction. So this is what the graphs would look like. Now, the reason I'm showing you these three graphs is that these are the three graphs for zero order, first order, and second order, and we're going to look at each one of them. So the justification for this, if you are asked to justify if this is a zero order reaction, it would be this sentence right here, okay? The plot of concentration of A versus time produces a straight line. That's your justification for zero order. And so you can see that right there. Okay, so based on the graphs, how do we know this is a zero order reaction? Because the graph of concentration versus time is a straight line, as I just talked about. An example of a zero order reaction would be the breakdown decomposition of N2O via platinum. The rate law here would equal K. And so then, your rate is equal to your rate constant. Then this is your integrated rate law there. Things to note about your zero order reactions. If you change the concentration, it does not change the rate. It is only it is the only direct straight line plot of the orders, and rate is always equal to your rate constant. Again, I do want to remind you a couple things about rate constant. Rate constant depends on temperature, and it also depends on the specific reaction that is being explored. First order reactions. So the integrated rate law for first order reaction takes the form. Let's look back at the equation sheet again. It's going to make sense to you. This will be the next one in the line. So it's this one. Okay, so the natural log of A at time t minus the natural log of A at time naught is equal to negative kt. So again, you're going to see this negative slope. So important things to notice, this is the equation of a line if you rearrange it where you have natural log of A is plotted versus time, and the resulting graph is a straight line. Then that reaction is first order, and the slope of that line is equal to negative K again. So if we rearrange, then again, you get the equation for a line. If, again, you know the concentration of A at time naught and the rate constant, then you can calculate the concentration of A at any time, but you'll have to take the natural log of this concentration of A at time naught. So then we can also, this is a line in your notes. This can be expressed as a ratio of the concentration of A to the concentration of A sub naught, like this. And that's because this is an exponential expression, natural log. I don't see you needing this. I had it in my notes because I believe this there used to be a second form of the first order reaction on the equation sheet, but that's kind of outdated now, and so probably you don't need this anymore. So moving on along from that. First order reactions, if we have our three sets of graphs again, the first order reaction will be this one in the middle, because this one forms a straight line when you graph the natural log of A versus time. So then if you were to look at an example here, again, we know this is first order because the graph of natural log is is a straight line. The example is the hydrolysis of cisplatin. So you can see it looks like this. And so over time, cisplatin concentration decreases, and you see we have a curve here, and then the concentration of chloride increases. And so it's this curve that when you take the natural log of that, you get the straight line. Okay, so your rate law, this is your differential rate law. Rate is equal to K times the concentration of A. For your integrated rate law, you have the natural log versions of that. And then things to note about first order reactions. It is the only order with a constant half-life, and this is really, really important. We're going to talk about this more in just a second. And the units of K is equal to 1 over whatever your time unit is. Now, please do be very careful. You need to pay attention to that time unit. Seconds, minutes, hours, days, weeks, months, years, any unit of time could apply here. Now, the ones that we see most often tend to be seconds, minutes, and hours. I have seen students default to using minutes or using seconds when that was not the unit given, and they miss a point because they just make an assumption about what the time unit is. So please don't fall into that trap. Radioactive decay is first order. They make a note of this in the AP course and exam description, which means I'm making a note of it here for you. That means that they could ask a question about radioactive decay and expect you to know that it is first order. And then, of course, we can also tie this into the knowledge that radioactive decay has a constant half-life, which you might know just kind of from life because you hear about half-lives of things being described. And so they only give you this one, they say the half-life of, what this thing is this amount. And so that is a constant half-life then. Okay, so the half-life of a reactant is the time in which the half of the reactant is consumed. So it looks like this. So after one half-life, you've decreased by half. After a second half-life, you've gone down to 0.25. After third half-life, you've gone down to 0.125, and so on and so forth. Every time you go through a half-life, then half of that reactant is consumed. So half-life calculations vary with the order of the reaction, but the half-life of first order reaction is again found on the equation sheet at top in kinetics, and it's this one right here. So your half-life is equal to 0.693 over K. Again, this is only true for first order reactions. Zero order and second order actually are not constant, so they depend on concentration, but you don't need to worry about those. So if we look at an example of radioactive decay, you can see that after one half-life, we go from 10 grams to 5, and then after two half-lives, 5 to 2.5, and so on and so forth. And so then you can actually do calculations about how long a species has been decaying or how many half-lives it has gone through if you know the amount of radioactive or the amount of original substance that remains. So notice that for a first order reaction, again, the half-life is constant. So this is really important because this is one way that you can justify if a reaction is first order. If you cannot look at a graph and determine if it is first order, if you don't have a study of initial rates to determine if it's first order, you can look at half-life. And if you know that the half-life is constant, then you can identify that it is first order. Okay, so then also as a note, you only have to do half-life calculations for first order reactions in AP chemistry. All right, second order reactions, the integrated rate law takes, again, we're going to come back to our trusty equation sheet. It's going to be the third one here. 1 over the concentration of A at time t minus 1 over the concentration of A at sub naught is equal to KT. So important things to notice here. In this case, the plot of 1 over concentration of A versus time will produce a straight line with a slope equal to K. So this is our only positive slope. So then if we can do 1 over the concentration of A sub naught and the K, then we can calculate the concentration of A at any time. So you notice that this bullet point is a little bit repetitive, but I do want to put home this idea that if you have this value and you know the rate law and you know the order, you can always calculate the concentration of A at any time because they will ask you sometimes to do that on the exam. So based on the graphs, how do we know this is second order? Because the graph of 1 over concentration versus time gives you a straight line. And you can see that if I move my head out of the way. There you go. Example of a second order reaction is the dimerization of this species here. And so we can put 2 of those together. That would be second order. And that means that 2 of these have to meet, which is kind of the definition of dimerization. So rate law, rate is equal to Ka times the concentration of A to the power of 2. Again, here's your integrated rate law with the 1 over concentration values. Things to notice about second order, it's the only order with a positive K value for slope. The units of K are equal to liters over moles times second, or again, whatever your time unit is. So finally, this is a really nice summary of the 0 order versus first order versus second order. So the second row here is if you just look at raw data of concentration versus time and you graph it, this is more or less what it would look like. You'd see straight line for 0 order, a curve for first order, and a steeper curve for second order. And then the straight line plot to determine the rate constant, concentration versus time directly for 0 order, natural log of concentration for first order, 1 over concentration for second order. You can see all of those written out here. These are all on the equation sheet. Relative rate versus concentration. Your rate would not be changed for 0 order if you change the concentration of A. Your rate would change in the same way for first order. So if you double it, the rate would double. If you triple it, the rate would triple. And then for second order, it would be squared. So if you double it, the rate would be quadrupled. If you tripled it, the rate would be multiplied by 9 because that would be 3 squared. And then half-life, we do not need to worry about 0 order. We do not need to worry about second order. We only need to worry about first order, and this is again found on the equation sheet. And then finally, your units of K for your rate constant. It would be molarity per time, whatever your time is here. For first order, it would be 1 over your time. And then for second order, it would be the inverse of molarity over time. So that would be liters over moles. And then time is also in your denominator. Okay, so what should I be able to do with this? Well, you should be able to determine the first order of a reaction by examining the graphs of concentration of A versus time, or natural log of A, or 1 over A. And then again, that justification is that full sentence. This is blank order because the graph of A, natural log of A, or 1 over A versus time shows a straight line. You should use the integrated rate law corresponding to the order of a reaction to determine the value of K. You should recognize that the half-life of a first order reaction is constant. And you should be able to apply the half-life equation for a first order reaction to determine the value of K, or to determine the half-life of the reaction, including the process of radioactive decay. And I do want to come back up here to the second bullet. So I said use the integrated rate law corresponding to the order to determine the value of K, but you can also, as we've talked about, if you know your rate law K, your rate constant K, and you know the concentration of the species, you can use, and the order, you can use those to calculate the concentration at any time. And that is a really useful thing about the integrated rate law as well. So I've had students ask me, just kind of a side note here at the end, when do you use the differential and when do you use the integrated? And the big difference between the two is that inclusion of the factor of time. So with the differential rate laws, we're using the method of initial rates. And so we're kind of taking the time out of it because we're looking at a rate and we're looking at it initially right as the reaction begins, so that you don't have to worry about that reverse reaction. Whereas with the integrated rate law, we're studying the change in concentration and the change over time. And so that is the big difference there. So if you see concentration and time data, you're going to use an integrated rate law. If you see concentration like multiple trials with concentration information and rate information, then that's going to be differential. And so that is it. Kind of a long video, but there was a lot going on in section 5.3. Section 5.4 is much shorter, and I'll see you soon for that.